introduced a symbol called Kroneker's delta. So this is Kroneker's delta, and the definition goes something like it's 1 if I equals j, 0 otherwise. So this is actually a second order isotropic tensor. Now we'll define what are tensors, second order tensors, and then we'll briefly look at what are isotropic tensors. Okay, so tensors are defined as quantities. So there's a very nice way of defining these vectors, tensor, etc. So what do you think is the definition of a vector? What is the definition of a vector? Whatever you have covered, what do you know? Okay, anything else? Anyone else who wants to take a jab at it? So, when we were doing our graduate studies, our professors used to say a vector is a vector. That's the definition of a vector. A tensor is a tensor. So, basically, in continuum mechanics, these are such fundamental quantities that you can consider their definitions to be basically axiomatic. Axiomatic meaning you don't need to define them in terms of something else, they are fundamental quantities in their own right. Okay, one of the fundamental property which is used to identify if something is a vector or a tensor is, as your friend said, that they behave under certain ways under transformations. So for example, last time we had looked at that if you have a Cartesian coordinate system e hat 1, e hat 2, e hat 3, and let us say you transform it to e hat I primes basically, then we saw that for, let us say, a vector v or a, whatever we took, so vi e hat I, we can also write it as vi prime e hat I prime, and then we can take a dot product with e hat j prime, and then this quantity basically is your Kroneker's delta. So this is vi prime delta ij, and then vi e hat I dot. Okay, and then we can write this as vj prime is vi, and then I can write this as, let's say, aij. Okay, so let us say we define this aij as e hat I dot e hat j prime. Then a tensor is a quantity, let's say any order tensor is a quantity, let's say I define that tensor. So I'm going to write a vector with a single underline, a second order tensor with a double underline. So you can think that I'm writing a general nth order tensor. Then this is going to be, let's say, t I j k, whatever order is there, and then e hat I, e hat j, e hat k, whatever is the order. Okay, so this is how a tensor is represented mathematically. It will be represented mathematically for us, and we'll call it a tensor if under this kind of a transformation I can write down its transformed components t prime p q r as a p I, a q j, a r k, so on, and then t I j k, so on. So for us, any quantity that follows this behavior under a transformation of the coordinate system will be labeled as a tensor. Okay, any quantity that undergoes this kind of a, now it might look like, shouldn't all quantities behave like this? So I'll give a nice example. Let's say you have, do you guys know what this symbol is? Huh? This is a gradient or the nabla symbol. Let's say we define, so usually for Cartesian coordinate systems, this nabla operator is defined as e hat I del by del xi. This is the definition. Okay, we'll look at this briefly in a few moments. when we look at tensor calculus. So this is E hat I del by del xi, and you can look at the optional section of chapter 1 that I have uploaded, and you will see that this guy doesn't transform like this, okay, or if you want to write it like a vector, this guy doesn't transform like a vector. So even though we have done something which we are used to doing for vectors, that is, we have written its components and expanded them in some basis vectors, but it's not a vector. This grad operator, nabla operator, del operator, whatever you want to call it, it's not a vector. Okay. So for those who have this intuition that this is going to be perpendicular to A, that's not the case, because grad is not a vector, and actually for general fields this is not equal to 0. Okay. When we look at continuum kinematics and fluid kinematics, we'll define a very, I'll give you a very specific case of a velocity field in which this quantity is not 0. Okay. So this is not in general 0, because this guy is not a vector, because it does not transform like the property we want them to. Okay. So this is how we identify things as tensors. Now an isotropic tensor is something which should tell you by its name that if I rotate the coordinate axis in any way, then the components are not going to change. Okay. The components are not going to change if I rotate it under any rotation matrix, or rotate these guys under any rotation matrix. So delta ij, or for any scalar times delta ij, this is a second order isotropic tensor. Second order meaning it needs two bases to be defined. Okay. If you have E hat I, E hat j, then you will write it like this. By the way, I have just, so there is no dot in between them. This is not a multiplication. This is not a cross product. This is a simple juxtaposition of your unit vectors. What does that mean? It's just E hat j next to E hat I. If you want to be very rigorous, then the correct way of writing this is E hat I tensor product E hat j, tensor product E hat k, and so on, where this tensor product is something which you can visualize very neatly if you look at. So let's say E hat 1, and let us go back to our visualization of these vectors being column vectors. Okay. So E hat 1 in that case is going to be 1 0 0. Okay. Let us look at E hat 2, which is going to be 0 1 0. Then E1 tensor E2 is defined as E hat 1 E hat 2 transpose. Okay. So this is a 3 cross 1. This is going to be a 1 cross 3. What is the product of them going to be? A 3 by 3 matrix. And imagine you can imagine very easily what are the components of that 3 by 3 matrix going to be. What are they going to be? So what is this E1 E2 transpose going to be? Hmm? What is it going to be? Can do matrix product now. 1 0 0 times 0 1 0. What is this going to give me? Huh? What is the first entry going to be? This one. Then and now, huh? All zeros. And then, okay. So this is what E1 tensor E2 means. So you can imagine that this E1 tensor E2, okay, it's using the ones and zeros to define a general second order tensor. Okay. How do we define a first order tensor, which is a vector, by the way? So vector is a first order tensor. Let's say, let's write it here. Vectors are first order tensors. For a Cartesian vector, for a 3D Cartesian vector, how many independent components can we have? 3, right? So E1, E2, E3 are going to basically permute this 1 and going to give you, let's say, x I cap plus y j cap plus z k cap as x times 1 0 0 plus y times 0 1 0 plus z times 0 0 1. So, we have converted a general vector into a linear combination of 3 independent vectors which are the bases. Okay. So, all of these things relate very nicely to the vector spaces which you might have studied in linear algebra. So, this tensor product is doing the same thing. So, instead of 3 independent vectors or 3 independent tensors, how many independent tensors will you need for a second order tensor? 9. Okay. And you will have a 1 in place of a component in each of those 9 independent tensors. Okay. So, it's sort of like it's defining, okay, what is the particular component in a particular direction, okay, and rest all I'm going to ignore, and it's adding those components one by one. There's a very nice infinite dimensional version of this which you guys know, which you guys call as functions. Okay. How do we usually define functions? We say, what we will say is, you can represent functions also as linear combination of some specific functions which behave like these bases. Okay. I won't go into that into the details of that, that's outside the scope of this course, but you should have a very good intuition of what this guy means. So, from here you should be able to extend what a general nth order basis tensor will mean. Okay, a general nth order tensor. So, for third order tensor, how many bases you will need? 27, and in each of the component you will have one or other 0 in each of those 27 bases. Okay. Now, a third order isotropic tensor is defined using the symbol called epsilon ijk, which is called an alternating tensor, or in some textbooks you may see it being called as Levi-Civita. There are other names also which I don't remember. So, epsilon ijk is basically defined in in very similar ways as delta ij. So, it is defined as 1 if ijk follow a cyclic order. So, if ijk is equal to 1 2 3 2 3 1 or 3 1 2. Okay. So, it is going to be 1. It is minus 1 if ijk are equal to 1 3 2 3 2 1 3 2 3 2 1, and what is the other going to be? 2 1 3, and it's going to be 0 otherwise. Yeah. It's not a matrix, no. It's not a second two. It's not a 2 by 2 or 3 by 3 matrix. It's a cube. It's a cube. And then you have to repeat it. So, let's say you want to consider E1 tensor E2 tensor, let's say E3 again. Okay. So, E1 E2 you can imagine it's a matrix, and then E3 is multiplying that. So, basically you have to repeat E1 tensor E2. So, E3 is going to be 0 0 1. So, let's say this hand represents this E1 tensor E2 times 0, E1 tensor E2 times 0, E1 tensor E2 times 1. So, then you get a cube. And, I don't know. I don't need that for fluid mechanics, so I don't care. Actually, we'll need that, but we don't need to visualize it. So, we don't need to visualize them. We will, when we discuss Newtonian fluids, we'll look at fourth order tensors. You guys have done elasticity, right? So, you know a general elastic tensor is fourth order tensor, because a strain is a second order tensor, a stress is a second order tensor. So, in fluids, we are going to go down a very similar route, but instead of strain, we are going to have strain rate. That's it. That's the only distinction between undergraduate level solids and fluids. It's just that in solids you have strain, in fluids you'll have strain rate, as long as you're discussing very classical solids. Sometimes people discuss viscoelasticity, where you have both strain and strain rate also, but that's not a, that's a matter of an advanced course. So this alternating tensor, there is another way of defining this alternating tensor, and for that let us look at the cross product. So E1 or EI cross EJ, okay, is written as epsilon I j k E k. So instead of this kind of a cumbersome definition, you can relate epsilon I j k to the cross product of your Cartesian vectors. Something very similar to what we did for delta I j, we define it as E I dot E j. Okay. So E I cross E j, you can define it like this. Okay. This is very straightforward, right? Because if E I cross E j, what is the component of E I cross E j going to be along either of these? What is it going to be? 0. So if k is either equal to I or j, epsilon I j k is going to be 0. Okay. And you will need some other, so E1 cross E2 is going to give you 1 in direction of E3, and similarly E2 cross E1 is going to give you -1 in direction of E3. Okay. So basically it's a way of encapsulating this complex definition using index notation and Cartesian vectors. This is also helpful when you have to write the cross product of two vectors or any tensor. I'm going to give you a lot of examples through vectors, but it should be straightforward to extend them towards any other tensor. So let's say you want to look at a vector which is defined as A cross B. Okay, we have A cross B. So you have, so this is look at the steps, these are important. Okay, they may feel trivial for this kind of an example, but as we move further for as we move further in calculus direction, when we look at gradient, when we look at curl and all those things, these steps are important. Okay, so pay attention. So A vector I am going to write as EI, AIEI cross. Now can I write BIEI? Why? Why can I write, why can't I write BIEI? Right? I cannot do any repetition beyond twice. So I cannot write BIEI. So let's just choose something else. Let's say BJ, EJ. Now AIs and BJs, these are scalar. The order of multiplication of these components doesn't matter. What matters is the order of multiplication of the basis vectors. Okay. So you can also write this as AI, BJ, E hat I cross E hat J, and you can also write this as A, BJ, AI, EI cross EJ. You cannot change the order of multiplication of the vectors. They are not, they don't commute, but the scalar multiplication will commute. Okay, and if it's not a cross product, it's a dot product, then the vector multiplication will also commute. So BJAI or AIBJ, whatever you want to write, and then I write EI cross EJ as that guy. So this is basically epsilon I j k AI BJ E hat k. And then C vector, let's say on the left hand side, I write as CL E hat L. Okay. So this is going to be a trivial manipulation, but I just want to highlight it in steps because it feels trivial for this example, because this example is trivial. When we move to more complicated examples, same steps will apply. So try to detach your intuition and just follow the algebraic steps. So CL E hat L is this. So I can take a dot product with, let's say, E hat M, and I'm going to write CL E hat L dot E hat M equals epsilon I j k A I B j E hat k dot E hat M. So this is CL delta L M equals delta K M. So this means Cm equals epsilon I j m A I B j. which I can also write. So, if these are maintained in the cyclic order, so I, j, k, if they are maintained in the cyclic order, so 1 2 3 or 3 1 2, so I can replace I epsilon I j m by epsilon m I j a I b j. So, mth component of this cross product is given using your alternating tensor. Mth component is defined using the alternating tensor. Now, there is an interesting property which I guess is the kind of property that you can write in your cheat sheets for any quiz or exams, and that is if you have a multiplication of these two epsilon I j k, let's say epsilon p epsilon I p q, then this is given by delta jp delta kq minus delta jq delta kp. Okay, it's usually called the epsilon delta identity. This will be very useful when you have two consecutive cross products. Okay, as you can imagine, one cross product introduces an epsilon, another cross product will introduce another epsilon, and if it just happens that their indices are in this kind of an order. So, usually it may not happen that your first index is the same on the other one. You may have a case where you have epsilon I j k times, let's say, epsilon p q I, okay, and you may have to swap the first and third indices to make it look like this so that you can apply the epsilon delta identity. Okay. In the similar way, a fourth order isotropic tensor can be defined. A fourth order isotropic can be defined using linear combinations. Let's say you want to define a fourth order isotropic tensor with the indices I, j, k, l. Okay. Then you can define a fourth order isotropic tensor using linear combinations of delta I, j, delta k, l. Let's say C1 times this plus C2 times delta Ik delta JL plus C3 times delta IL delta JK. You can think of this fourth order isotropic tensor as a tensor product of two identity matrices, let's say. Okay, if you can ever visualize four dimensions, then you can visualize it as a tensor product of two identity matrices. Okay, but I mean that's very hard. So you don't have to memorize this. You just have to take some let's say an intuitive feeling of what's going on with these deltas. Okay, what we are trying to say is that delta ij is what is we have is something we have recognized as a isotropic second order tensor. So I'm going to use that to maintain isotropy in two directions at a time. If you have four directions, four dimensions, I am going to use the delta ij to maintain isotropy in two directions at a time. So, first you maintain isotropy in ij and kl at the same time because they are multiplied. Then you maintain isotropy in ik and jl at the same time, and so on and so on. Okay. So, you sorry, these are not tensor products, but so I have written just the component of a tensor here. This is a component of a tensor. Technically, this will have to be C I j k l, E hat I, E hat j, E hat k, E hat l. And then you will have to define it as C1 times delta I j, E hat I, E hat j times delta k l, E hat k, E hat l plus so on. Okay, just to prevent myself from writing these cumbersome basis vectors, I just wrote the components of this tensor. Okay, and this is something that we will try to do a lot in the fluid mechanics course, because sometimes it becomes very cumbersome to carry on these unit vectors all the time. While we are doing this index notation, reviewing this properly, and let's say you are giving a solving a question for index notation, then doing this will be important. But when I later go down into fluid mechanics derivations, then I may skip writing these basis vectors. Okay, if you're confused, just ask me, but if you understand whatever I have skipped, then you understand it. Okay, so you don't have to memorize this. Okay, I'm just giving you a flavor of what is going to come later down the line. And now using these tools, you can do a lot of tensor algebra. Okay, you can do a lot of tensor algebra, where basically we are doing multiplications, addition, subtractions, and so on. For example, you can simplify something like, let's say, a dot b cross c. Okay, you can simplify this you guys know as a scalar triple product. You can simplify this kind of a quantity, a cross b cross c. Okay, you can simplify this using index notation. So let's do a cross b cross c. So how are you going to write a cross b cross c? So let's first write ai e hat I cross bj e hat j cross ck e hat k. So all the scalars, you can combine them together. Their order of multiplication also doesn't matter. So this is eventually e hat I cross e hat j cross e hat k. How do I simplify this? How can we simplify this using the tools that we have looked at? Hmm? So E hat j cross E hat k is epsilon j k L E hat L, right? So I can substitute this E hat j cross E hat k using this. So what do we get? Again, this part itself is a scalar, so this can be epsilon j k L A I B j C k. And now what do we do? So epsilon j k L epsilon I k p, let's call A I B j C k. Huh? E hat p. And now we can use this, but to get to this, we have to do some reordering. So I can write epsilon j k L as what? Epsilon k L j, and this guy k p I. And now we can apply our epsilon delta identity, and that is going to be delta LP delta JI minus delta LI delta JP AI BJ CK E hat P.
On the third step, it should be EI cap into E. Instead of K, it should be L.
Where?
Third step.
थर्ड स्टेप कौन सा है यार, मेरे को बताओ जरा. This one.
Oh.
You're right. Thanks. So that changes. So E hat I cross E hat L will be actually this. Hmm? So KLJ, and then actually instead of KLJ, we'll have to convert it into LJK, and then this will be LPI. Actually, we'll get a minus of this, but we can write down the things again. So this becomes delta Jp delta Ki minus delta Ji delta Kp. Is this fine? Okay. So what does this simplify to? I we can replace with K, and J and P we can interchange. So what do we get? AK Ck times BP E hat P minus, now I and J we can interchange. So AI BI times CP E hat P. And this is the thing that you probably have memorized. A cross B cross C is what? A dot C times B minus A dot B times C, right? That's what you get. Okay. So look at the steps here carefully, because these steps are going to be useful now when we discuss tensor calculus. I mean, we are not going to discuss tensor calculus in detail, we are just reviewing things, whatever is required for this course. Before we go to tensor calculus, I just want to highlight that, let's say you have a second order tensor, let's call A, and let's say this is Aij E hat I tensor E hat J, then it is possible, just like it is possible to break a second or square matrix into a symmetric and an anti-symmetric components, then it is possible to write this down as Aijs, let us say, plus let's say Aij prime, okay, or you can think of it like, let's say Sij E hat I tensor E hat J plus Rij, where Sij is equal to Sji, your symmetric second order tensor, and Rij equals minus Rji, your anti-symmetric second order tensor. Okay, it is possible to break a second order tensor like this. So how many independent components is the symmetric component going to have? Huh? 6. How many independent components is this anti-symmetric going to have? How many independent? 3. 3, right? There are 3 independent components that an anti-symmetric second order tensor can have. Okay. What about the diagonals? What about diagonal of A and diagonal of S? They'll be the same, because the anti-symmetric part doesn't have a diagonal, right? Diagonal entries are 0. So these are things which will be useful in a moment when we discuss continuum kinematics. Okay. One important thing that I'm going to ask you to remember is that there are 3 independent components of a second order tensor, which means there has to be some way in which we can write it as a vector. Okay. Now I'm not asking you to write the second order tensor as a vector. There must be some vector which can be converted, or whose components can be brought into the positions of your second order antisymmetric tensor. Okay. So there has to be a relation between an arbitrary second order antisymmetric tensor and a vector which is made up of its 3 independent components. Okay. So let's say you have an antisymmetric second order tensor which has 0 0 0, you have A B C, so you'll have here what, minus A minus B minus C, right? there has to be a relation between this, and we'll not discuss the relation just now. Okay, I'll just write it as a question mark, and there has to be some relation between this tensor and this vector. Okay, what that relation is, we'll discuss that in either this class or the next class. But the name of this vector, which is made up of these three independent guys of a second order antisymmetric tensor, this is called a dual vector of this tensor. Okay, it's called a dual vector of this tensor.
Then how did you club A with E1? Why is it not?
That's my choice. It's my choice. There's no particular reason why I did that. Okay, that's just a choice. That's a good question actually. Why this? So now let's review tensor calculus, and the central quantity or property or whatever you want to call it that is going to be useful for us is this nabla operator, which we define as E hat i's del by del x i's. Okay. Now if you look at the optional section of chapter 1 that I have uploaded, you will see that this nabla operator is also not this innocent, but as far as this course is concerned, it is really this much only. Okay, here these E hat i's are the Cartesian bases or unit vectors, whatever you want to call them. Okay, so it's really going to be only this definition is going to hold in Cartesian bases only. When you change your coordinate system from Cartesian to, let's say, cylindrical or spherical, it's not something similar. It's not that straightforward. You're going to get E hat r del by del r plus E hat phi del by del phi. No, there are additional quantities which you have to account for, and you can read about them in the optional section of chapter 1. And ideally that's how a continuum mechanics or a fluid mechanics course should start, but that's okay. So this is how we define this operator. We'll call it a nabla operator. Sometimes we'll call it del, or sometimes we'll call it a grad operator, but it's not really a grad operator because gradient depends on what sign you have next to it. So this is something that I will try to refrain from. Okay, and using this we define, let's say, a quantity del dot A, where this A is a field now. It's a field, that is, the components are something like this. Okay, so A is a vector field or a vector valued function, you can think of it, which is different at different spatial points, and for that I can define this operation with a dot product in between. It's called divergence of A. Okay, you may see it written as in some textbooks like this, and by definition of this dot product, again, what I'm going definition of this nabla operator, I'm going to write it as E hat I del by del xi dot aj E hat j. So again, what does this simplify to? So this is del aj over del xi E hat I dot E hat j, which is what? Del aj by del xi delta ij, which is what? Huh? Del ai by del xi. So it is actually a summation of 3 terms. Okay, this is actually a summation of 3 terms. This is del a1 by del x1 plus del a2 by del x2 plus del a3 by del x3. Okay, by the way, just a trick question, what is delta I? Okay, it's 3. What about this? Delta I times delta JJ. Huh? 9, right? So these are things that you have to be very careful about. What about this? What about this? Epsilon ijk times epsilon ijk. 27. 0. This is not JE. You don't have to stick to the time limit. Just try to be rigorous. Huh? How? करो गैस लिया ना 6 हाँ करो करो ना फिर फटाफट करो वर्बलाइज दैट लॉजिक इफ यू कुड वर्बलाइज दैट लॉजिक यू वोंट हैव टू राइट इट you raised your hand 1 no
9.
no just apply the delta epsilon delta identity what see what you get so this is what delta jj times delta kk minus delta jk times delta jk what is this delta jj times delta kk what about delta jk times delta jk delta jk times delta jk is delta jj which is 3 okay like tensor also okay and the definition is something like this for a vector this becomes e hat I del by del xi of aj e hat j and this is del aj over del xi e hat I e hat j so for a vector the gradient of it of a vector field gives you a second order tensor Okay, gradient of a field gives you a second order tensor. It is very important to note which one of them, which one of the indices appears first. It's the differentiation that appears first. Okay, this is important because it doesn't matter if you visualize these as row matrix, row vectors, column vectors, whatever you want to visualize them, but the order here matters, because if these particular components, they are not symmetric, let's say this is not a symmetric tensor, then things can really become very confusing. Okay, so make sure that you understand from the definition of gradient which index comes first, the numerator one or denominator one. And similar remark here, for a vector field, the gradient is a second order tensor field. So, for an nth order tensor, the gradient is going to be an n plus 1th order tensor. Another operation that we can define is the curl of a field, and the curl is defined as del cross of A, where you get E hat I del by del xi cross aj E hat j, which again becomes del aj over del xi E hat I cross E hat j. And this quantity you can write using epsilon ijk. Okay, this is simply epsilon ijk E hat k, right? What is the order of the result? What order tensor is the result? First order only, right? So, a curl of a vector gives you a vector, curl of a nth order tensor actually gives you an nth order tensor. It is because you can write the cross product of these basis vectors as a linear combination of the same basis vectors. Okay, you can write the cross product of the basis vectors as a linear combination of the same basis vectors. Okay, so that's why we maintain the order of the tensor in a curl operation. Okay, any questions? So tomorrow we are going to start with continuum kinematics using these. Uh huh. Uh huh. Dot commute, so I don't care. So it's, you're right. Okay. You mean I can write E hat P dot E hat I? You mean this? Then yeah. Yeah. So that's why I tend to not write the tensor product, because it, tensor product is really just for visualization. It's really just a juxtaposition. If you have E hat I dot E hat P, E hat Q, E hat R, E hat any order, then it's the first dot product that matters. Okay. You can go ahead and simplify this yourself also. Just consider this. Try to consider this. Try to write, let's say, E hat 1 dot E hat 2 E hat 3. See what you get. Okay. You you will see that it doesn't matter if I write it like this or if I write it like this, which is what you were asking, I guess.